start recording. Okay, so let's see. Where are we? Here we go, y'all. So we're actually in week 11. Man, I can't even believe it. We're week 11, y'all. Just a few more weeks to go. So let's see. What I have here, y'all, is the information that what we're doing this week. Again, this is all just the standard protocol stuff. Y'all, so I think from here on out, we can probably slow it down a little bit to where we basically do one section a day, no more of this like 1.5 stuff. I think we can probably do it that way. There might be another week where maybe we gotta, do the 3, but the pace should be pretty comfortable. Anywho, y'all, this week we're doing 2 sections. We're doing 4.10 and 5.1. So today we're gonna go over 4.10. The homework for 4.10, y'all, is due a week from tonight. And then I do have a quiz over chapter 4, y'all. The quiz is not due until next Wednesday. Okay, originally I had put that it was going to be due Monday, and I don't know, when I woke up this morning, I don't know why, but I thought about it, and I was like, why don't we push it till Wednesday? This way you have a few more days to do it. It's 10 questions, y'all, just like quiz 1 and 2 had, okay? And it's over chapter 4, okay? Let's see. Wednesday, y'all, we're going to do 5.1, okay? We'll worry about that on Wednesday. Again, everything I'm recording, y'all, I will upload it to the playlist, and I've been doing that as we've been going along, okay? So I usually upload the videos, if not that afternoon, then the next day, but if you click on the playlist, just so you guys know, if you can click on the playlist here, you can see up to 4.8. Y'all, we don't actually do 4.9 in this class, so that's where we're going directly to 4.10, okay? It's just an optional section, but I opted not to cover that one just because I want to make sure that I do cover the topics that are absolutely essential. So let's see. 4.10, y'all, talks about these things called antiderivatives, okay? So let's figure out, it says, find the general antiderivative of a given function, explain the terms and notation used for something called an indefinite integral, state the power rule for integrals, and use anti-differentiation to solve simple initial value problems. All right, so let's take a look what we have here. It says a function f is an antiderivative, sorry, I should put it this way. A function capital F is an antiderivative of the function little f if f prime or capital F prime of x is equal to f of x for all x in the domain. Okay. What we're really doing here, y'all, we are going backwards. If we know what the derivative of a function is, what we're trying to do is figure out what would the original function look like. That's what an antiderivative is, okay? So it says, let capital F be an antiderivative of f over an interval I. Then for each constant c, the function f of x plus c is also an antiderivative of f over I. And then it says, if g is an antiderivative of f over I, then there's a constant c for which g of x is equal to f of x plus c over I. And then it says, in other words, the most general antiderivative of f over I is capital F of x plus c. Okay, before I even think about the first problem, I want you to think about this for a minute, y'all. I want to keep this really, really simple. Suppose I told you that we took the derivative of a function and we came up with 2x. What I want to ask you is, what was the original function? So then when we took the derivative, we came up with 2x. Do y'all agree that x squared would be the function? Because when we take the derivative of x squared, we get 2x. But y'all, I want to mention something here. Could my function have been f of x equals x squared plus 5? Okay. Could my function have been x squared minus 7? Yeah, it could, right? So what we say, y'all, no, not plus or minus infinity. What we say is the original function would have been f of x equals x squared plus some constant, because we know that the derivative of a constant happens to be 0, right? Because I know that if I take the derivative of this function and I take the derivative of this function, I would actually end up with that. So we actually have the antiderivative, y'all, we actually have an infinite number of antiderivatives because we can attach any constant at the end of that. Does that make sense? Okay, so the general form we say is my antiderivative is going to look like this. F of x equals x squared plus some constant because, again, the derivative of a constant would have given us 0. Yes, sir? Well, remember, it's not just integers. It could have been, that's the number. That's our constant because that constant, yeah, that's the official one. And if you notice right here, look what we have. F of x plus c, right? We have that constant. Yeah. Okay. Different c. Different c. Okay, so look, y'all, what we're going to do here is we're going to see if we can figure out some kind of a pattern, and then we're going to talk about some general rules that we're going to apply on finding the antiderivative. Okay, so I want you to take a look here. It says if f of x equals 8x to the third minus 4x squared plus 10x minus 5, and an antiderivative of f. Notice what they're saying. One of the antiderivatives, because remember, we really have an infinite number of antiderivatives because we can always attach a constant at them, is going to be f of x equals ax to the fourth plus bx to the third plus cx squared plus dx. Okay, so let's think about this for a minute. Y'all, look at the first term that we had here. The first term we had when we took the derivative was an 8x to the third. And we know that when we take the derivative, this number always comes down to the front and we reduce it by a power of 1. So if we're going to be going backwards, would you all agree that that would have been, instead of a third, wouldn't it really have been a fourth? Okay. And I had something here. So I had to multiply 4 by something to give me an 8. 2? Okay, so I want you to look at something here, y'all. Look what they're writing. They're saying, what is ax to the fourth? So a would be what number? A would be my number 2, right? You see the game I'm kind of playing here? Okay, we're going to do the same thing again. We're going to do the same thing for the second part. I want you to look at the next part. We have a bx to the third. So I have a bx to the third, and we used to have a negative 4x squared, and we know that that would have been an x to the third. So the question I want to ask you is, what did we have to multiply 3 by so that we would end up with a negative 4? Let me ask you a question. Could I do this? And when I multiply the 3 over here, and I reduce that by a power of 1, wouldn't this here cancel with that? Actually, I should have made that. It doesn't need to be a negative. And so that those 3's cancel, and now I end up with my negative 4x squared. Does that make sense? So what would my number in front here have to be? A negative 4 over 3. Does that make sense on how I'm going about this? Okay. Let's take a look at the next piece. So look what we have right now. We have a 10x. Okay. And we know that we're supposed to have a cx squared, right? So think about it this way. When I'm taking the derivative of this, y'all, isn't this really 2cx when I take the derivative of, say, cx squared? Wouldn't I really get 2cx? So wouldn't 2c be the same thing as what number? As the number 10, right? So if 2c is equal to 10, wouldn't c, oops, sorry, it's supposed to divide by 2. Wouldn't c really be the same thing as the number 5? So look, y'all, I'm going to put a 5 right there. Okay. And then I'm going to play this game one last time. Come back over here. Look what we have, a negative 5, and here we have a dx. So dx, and when I take the derivative of it, I get negative 5. So the derivative of this would just give me d equals negative 5. So shouldn't that number right here, y'all, be a negative 5? Okay, so look, I know I wrote all over the place, and I hate doing that because I usually try not to do that, but I did today for some reason. But I want to show you something. Look, we're going to do this. We're going to write f of x equals 2x to the fourth minus 4/3 x to the third plus 5x squared minus 5x, right? That's my capital F. And the little f of x is the same thing as capital F prime. And let's make sure that we did this right. So if I take the derivative of each of these pieces here, let's see, the derivative of 2x to the fourth should be an 8x to the third. When I take the derivative here, that 3 and that 3 will cancel. That'll give me a negative 4x squared. When I take the derivative here, that's going to give me a positive 10x. And when I take the derivative here, that's going to leave me with a negative 5. And is that exactly what we have right there? Right? So the antiderivative, y'all, is just asking us what was the original function if we had the f prime. Does that make sense? That's all the antiderivative is telling us. Okay. All right. So let's take a look at the second part that I have over here. So, and then we'll get into some kind of rules and regulations and all that kind of good stuff. Look what it says. Consider the function f of t equals 6t squared minus 7t. It says let capital F of t be the antiderivative of little ft. Then what would capital ft look like? So y'all, I'm going to ask you a question. I know I have a 6 there, so I'm going to go ahead and write my 6. Does anybody know what trig function do I take the derivative of and then it gives me a secant squared? Tangent. Very good. Because I know the derivative of 6 tangent t would be 6 secant squared t. Now, look at the next part. We have a negative 7t squared, right? That means that when we took the derivative, this is what we ended up with. So we know we're going to end up with a t to the third, right? Okay, so look, y'all, I'm going to call this, I don't know, a t to the third, right? Because I want to find the value of a. I want to figure out what this is going to be. I know that when I take the derivative with respect to t of this piece, I'm going to end up with a 3a t squared, right? Because 3 times whatever I have there is 3a, reduce it by a power of 1. So now look, I want to show you something. I'm going to set this part here equal to that number. So if 3a equals negative 7, do y'all agree that a would have to be negative 7/3? So then right here, y'all, I'm going to have a negative 7/3 t to the third. Okay. And at the very end, y'all, plus c. That c is what we call the constant of integration. That just means that we could have had a plus 2 at the end of it. We could have had a minus 1/2, something like that. We could have even had a plus pi over 3. And that still would give us that other function, the little f, as my derivative, right?
So sorry, the constant of origin?
Constant of integration.
Constant of integration.
Just means that you could have had another number at the end of that function so that when you took the derivative of it, you ended up with this function right here.
So what is that?
It's just a constant. It's just a real number, right?
Okay.
Yeah, it's just a real number because it just means you could have had something at the end of it. So when I took the derivative, I still ended up with that.
It's kind of a little bit like no source, like you have integers, all real numbers.
Yeah, all real numbers. Think of any number that, as long as it doesn't have an I, like imaginary numbers, it's a real number. Any number you can think of. 7, real number, right? 1/2, still real number.
Real number, what else? Complex numbers?
Complex numbers, which would be the square root of the negative, right, with the i's, right? Okay, so y'all, look what we have here. The next part, we're going to start talking about these things called indefinite integrals. Indefinite integrals. So this symbol right here is what we call an indefinite integral. It just means it's going to represent what we call the family of antiderivatives, okay? So remember, the little f of x is what my derivative looks like. Now we're integrating this function with respect to x. That's what that little dx means. So if you remember when we were taking derivatives, a lot of times, just like, actually I did it right here, but if you remember when we used like the chain rule, we would do something like this, like the derivative with respect to t, or even when we did implicit differentiation, we would have to bring in that dy dx type thing. This means that we're integrating the function with respect to x because f is the function that involves the variable x, right? This is what we call an indefinite integrals, and it represents what we call the family of all the antiderivatives, and it's equal to that antiderivative plus our constant of integration, right? Plus that c, okay? This is true if when I take the derivative of this function here, we end up with that little function on the inside, right? Kind of like what we've been doing with the last couple of problems. So this little symbol here, y'all, is what we call the integral sign. The function f of x is what we call the integrand. And dx indicates that the antidifferentiation is performed with respect to x, which is what we were talking about, okay? And then the arbitrary constant, here it is, John, is that constant of integration, okay? So again, if you notice here, y'all, it says, look, I'm integrating x squared with respect to x. So my function had to have been x to the third over 3. Why? Because when I take the derivative of this, I end up with that part right there, right? And again, the derivative of a constant is equal to 0. All right, so look, let me show you a couple of basic rules that we can use. This one here, y'all, is the power rule. Okay. Power rule says, remember when we were taking the derivative, we would multiply by that exponent and we would subtract 1? Since we're undoing the process, we're going backwards, we're going to add 1 to our exponent, and instead of multiplying by that number, we're going to divide by that same number because we're going backwards, right? So again, if before we would multiply by our exponent and then subtract 1 from it, the opposite idea of doing that is instead of subtracting 1 from the exponent, add 1 to it and divide everything by that new exponent, which is the n plus 1. Yes, this is going to, yes, for integration, Y'all, the integral of e to the x is e to the x plus c. The reason being, when we take the derivative, so if I told you like f of x was, I'm going to make this up, e to the x plus 7, and we find f prime of x, the derivative of e to the x is still e to the x. The derivative of 7 goes away. So all we're really doing here is if you say, okay, what function did I have to take the derivative of to get e to the x? Well, e to the x itself, right? And then we can add that constant. Let's see. Guys, if you notice here on the power rule, it says that my exponent cannot be -1. I want you to think about this one for a second. Look what we have, the integral of 1 over x. Isn't the integral of 1 over x the same thing as x to the power -1? Okay, when we do have that integral, y'all, it's the natural log of the absolute, yeah, absolute value. Guys, the reason why we put absolute value, the domain of the natural logarithmic function, actually any logarithmic function, says that the value of x here has to be positive. It can't be 0, but it has to be positive. Absolute value is going to ensure that my value is positive. Look what it says right here. X is not equal to 0, right? So even if x was a negative number, when we take the absolute value of it, it becomes positive, right? And if it was positive already, then we're fine. Okay. You can't find it. It's just not in the domain. It's not in the domain. Okay, y'all, just another couple of properties here. When we're integrating, if there's a constant in front, you can pull that constant out of the integral and then just find the antiderivative. And then if we are integrating either the sum or difference of two functions, we can write it as the integral of the first and the integral of the second, and then either add or subtract, okay? Either add or subtract. And again, we're gonna go through this in pieces, y'all. And then just a little bit, I don't know if y'all remember when we did this, and you know, if you don't, that's completely fine, y'all, but I'm gonna do something real quick here. I'm gonna come back to my Blackboard page, and I wanna say we did this in, I know it was in chapter 3. And I want to say it was in 3.7, but I'm not 100% certain, but I'm going to check it right now. 3.7, I think this, yes, it is. Okay, do you remember when we took, these were the derivatives of our inverse trig functions, right? Remember what we're doing now. Now we're integrating, right? So if I'm integrating something that looks like this, it would be the sine inverse of that f of x type stuff. And that's exactly what I have right here. We don't have all of them, we just have a couple. But there's a couple of rules here on, or little formulas on what happens if we're integrating a function and we're not sure, like, how would I do this? If it looks a little funky, y'all, chances are it's going to be one of these inverse trig functions, okay? So look, we're going to go through a few, I'm sorry? The derivative with respect to you. So just like we were doing over here, yeah, we were doing derivative with respect to x. It's just another variable. What did my notes go? Yeah, but I am zooming out. There, oh man, really zooming out there. Okay, let's see. Let me see. Where's the rest of my stuff? Where did the stuff go away? Yeah, definitely. Let me see. Here we go.
So the people like after Newton and
Uh-huh.
do they just like, do they have to, when they were doing the math, did they not simply out off the down the algorithm of the Hamilton equation? They have to do it like the one way that we did it before?
Probably. Yeah. Y'all, I don't know what happened to my notes. They kind of like, they broke. Yeah. So let me do this again. Let me just print it again.
Interesting. Maybe that's the reason why a lot of math is like, man, keep on having to do this math that's taking so long. Let's see if I can find shortcuts to this, you know?
Let's see. Okay, here we go. Better. Okay. So let's take a look here, y'all. We're going to find these intervals, okay? So look what we're integrating here, y'all. We are integrating the constant 3, okay? So let me ask you a question. What did we have to take the derivative of so that when we took the derivative, we ended up with just the number 3? 3x, very good. Okay, y'all, one thing I'm not going to forget, my constant of integration, right? Because it could have been 3x plus 1, it could have been 3x minus pi over 7. It could have been one of those, right? Or and a bunch of other ones. So we're always going to have that plus e at the end, okay? Very good. Now, let's take a look at the next one, x to the 7th. Remember what we're going to do, y'all. If I'm integrating x to the 7th, what we're going to do is we're going to add 1 to the exponent. So you all agree that's going to be an 8? And then we're going to divide by that same number, okay? So look, my answer here, y'all, is going to be x to the 8th over 8. One more thing. What am I missing? There you go. Plus the c. Y'all, I'm going to... C can be any number, right? That's why. So C can be, it can be plus -7, right? So look, y'all, look what it tells me. It says, remember to always check your answer by differentiating. So again, if I wanted to make sure I did this right, look, and we put a plus c here, and we take the derivative. Remember, that 8 is going to come down to the front. We're going to reduce it by a power of 1. Here's the 8 that I already have on the bottom. The derivative of my constant is 0. Those 8s will cancel, and we just end up with x to the 7th, right? So that's why, again, they're referring to that idea of, hey, check your answer by taking the derivative of whatever you think you got, right? Okay, so look, we're integrating now 1 over x squared. Can I write that as x to the power -2? Okay. So remember what we're going to do, y'all. We are going to add 1 to the exponent. So wouldn't that be x to the power -1? And we're going to divide by -1. And we are going to add our constant c, right? So right here, y'all, I'm going to put x to the power -1 over -1 plus c. Y'all, if you want to, we can also write it like this. If you don't want to use the negative exponent, you can write it as 1 over negative x, right? Because that negative is still down here on the bottom. It doesn't really matter where you put the negative. You can put it on the bottom, you can put it on the top. It don't really make any difference. You can write it like that. It's the same thing. With the top? Yeah. So there you go. Okay. Let me ask y'all a question. What do I need to take the derivative of so that I end up with a sine function? Okay. Yes, a negative cosine of x plus c. Again, think about it, y'all. I know the derivative of cosine of x is equal to a what? Negative sine x, right? So if the derivative of cosine x is equal to a negative sine x, then I have to take the derivative of a negative cosine x to get that positive sign, right? Okay. All right, I think we did one like this a little while ago. What trig function do I need to take the derivative of so I get a secant squared? Tangent x, very good, plus our constant of integration c. Okay. All right, now let's take a look at this one. What do we need to take the derivative of so that we get e to the x? E to the x, good, plus c. Now, y'all, I want to point something out. Look at the one that I have underneath. It looks almost identical to what we just had. Okay, almost identical, except it's not just e to the x. It's e to the 1/8 x. I want you to think about this for a little bit. If I were to take the derivative of e to the 1/8 over, or 1/8 x, okay, let's see. Well, we know the derivative of this is just e to the 1/8 x, but then I have to take the derivative of the angle. What is the derivative of 1/8 x? 1/8. Very good. Okay, so that's what we would end up with, right? We would end up with, if I took the derivative of e to the 1/8 x, I would end up with 1/8 e to the 1/8 x, right? But I want to show you something. Look what we're integrating. We don't have that part, right? We don't have that part there. How would I be able to cancel this 1/8 out? 8 over 1. Okay, so look, y'all. Now what we're going to do is we're going to say, look, if I had the derivative of 8 e to the 1/8 x, I would have 8 e to the 1/8 x, and then the derivative of my angle would have been a 1/8, and then those 8s would have canceled, right? Does that make sense? So what do I need to put in front of my answer? The 8. Does that make sense? Did I lose Jennifer? Am I okay? We're good? Okay. Okay, I just want to make sure, y'all. Remember what we're doing here, y'all. We're kind of playing a game. We're asking ourselves, what do I need to take the derivative of so that I end up with whatever I have right over here? It's kind of like inductive reasoning, right? Or intuitive reasoning, yeah. Y'all, anybody know what's the derivative of 1 over x? And again, if you don't, it's okay. I'm going to show you something. Come back over here. Look at look at the third one. What is the derivative of 1 over x? There you go. So all I'm going to do, y'all, I'm going to scroll back over here, and I'm going to put this is the natural log of the absolute value of x. Let's see. Okay. So I'll put it this way, y'all. This is, I think, probably going to be the most common experience that I think we're going to have in this class. When we have powers, when we have just like pieces of a polynomial or polynomial terms, x to the 8, 3x to the 6, something like that. Those are probably going to be pretty easy for us to do because we can use this power rule that we have right here, where, let me scroll back to it.
7.
Yeah, where we add 1 to the exponent and we divide by that new power now, n plus 1. Okay. I think the other ones who we're probably going to be pretty familiar with are, at least I'm hoping, are like, what's the derivative of, or the integral of sine x? I hope we can say, well, look, I know when I take the derivative of cosine, I get a minus sign, so this has to be a minus cosine. Or like secant squared. In our class, we've taken derivative of tangent, like that's probably the one we've taken the derivative of sine, we've taken the derivative of cosine, and we've taken derivative of tangent. Like how many times did we take the derivative of cosecant? Maybe one time when we did the one problem that had a cosecant, right? But it's not one that we used like on a regular basis. I think the e to the x one, if it's just e to the x, hey, that's really simple. If it is e to the power, and guys, look, we'll even do it this way. If it's a power, we will be able to figure out, hey, how do I do it when it's e to the power? We'll do that in a second. The 1 over x, y'all, you'll see a couple of problems like that, and then after a while, you'll kind of remember, oh, that's going to be the natural log of the absolute value of x. Those are probably going to be the ones we're going to be the most comfortable with. Some of these other ones, maybe we will, maybe we won't, but we'll figure them out as we go through. So let's take a look at this next one here. It says evaluate again the indefinite integral. So y'all, first thing I'm going to do, can I think of this as x to the power negative 1/2? Okay, so remember what the power rule says, y'all. When I'm taking my integral, I'm going to add 1 to my exponent. So if I take x to the negative 1/2, negative 1/2, I'm going to add 1, and then I'm going to take that same exponent, negative 1/2, and add 1 to the bottom, right? Because that's how we've been doing. Question, anybody know what is negative 1/2 plus 1? 1/2, very good. Okay, and negative 1/2 plus 1 again is still 1/2. Okay, next question. How can I write the power of 1/2? What is the power of 1/2? Anybody know? Square root, good. Square root of x. Does anybody know how would I simplify dividing by 1/2? Multiplying by 2 plus my constant of integration, right? Because when you divide by 1/2, it's the same thing as multiplying by 2, right? Okay, so look, here's a little repeat. What's the derivative of secant squared? Tangent of x, again, plus c. Okay, so y'all, I'm going to do a little copy and paste here because I want to show you guys something that, again, unless we have these formulas, they're not necessarily something that we think about on, like, something that we can kind of just look and say, oh, that's what it is. Okay, so look, I'm going to copy this here, get rid of that, scroll back down, here we go, and let me paste this. Yeah, and that's exactly why we have these formulas here. Okay, so here we go. Okay, so y'all, I'm going to give you a hint. The problem that we have here is going to be using one of these formulas here, the first one, right? Why the first one? Because we have the what in the middle? We have the minus, we have the square root, and we have the minus, right?
Why isn't that the bottom?
Let's see, why couldn't it be the bottom? Oh, because look at the order of your variables. It's u squared first and then a, where u is the variable that I'm using, and here we have our x coming second. Okay, so y'all, I'm going to ask you for a flavor. What is the value of a here in my problem? 1. Or a squared would be 1, so a is actually going to be the same thing as the number 1, right? Okay, what is the value of u in my problem here? U is the same thing as x, right? Does that make sense on what I'm doing so far? So look, y'all, all I'm going to do, a little stare and compare, and I'm going to say, I'm going to write my answer like this, which would be the sine inverse of u, which we're calling x, divided by a, which we said was the number 1, plus c, and that's really just the sine inverse of x plus c And that's going to be my answer. Okay. So they are. It's just, I happen to say sine inverse, but you might get a professor when you take Cal 2, your professor might say arc sine. Yeah. So guys, when you're doing your homework, you're going to see a problem like this, and it's going to, again, you're going to end up using one of those, 3 formulas right there, right? And it's really going to be a stare and compare type thing. And you're going to say, okay, what's the value of A, or what's the value of A squared, and then we can find the value of A. And then what's the value of U squared, and then what's my value of U, and then we can kind of play with it from there. Okay. So let's take a look. We got a few more to go here. Let's take a look at this one here, y'all. It says, suppose f prime of x equals negative 10x to the 9th minus 7x to the 7th minus 7x to the 3rd minus 3. And then it says, what particular solution satisfies f of negative 1 equals 27 over 8? I don't know, but what we're going to do is this, y'all. We are going to take the integral of negative 10x to the 9th minus 7x to the 7th minus 7x to the 3rd minus 3. Yo, just give you a heads up. When you write these integrals, they always put it in parentheses just to let me know that I'm integrating the entire expression, not just kind of like that first one. Okay. So look, let's use our exponent rules. Okay, so I have negative 10x to the, remember what I'm going to do with that power? We're going to add 1 to it, right? So that would be 10. And we're going to divide it by that same power right there, which is also a 10. Okay. Then we're going to do the same thing over here. We're going to go negative 7x to the power of 8, and we're going to divide it by that same power of 8, right? Because we're always adding 1 to my exponent. Y'all, I'm going to go back and we'll do some simplifying in a second. I'm just writing out the original problem now. Okay, negative 7 again, x to the power of 4 all over 4 minus 3x, okay, plus c, right? We always have that constant of integration. Okay, so look, y'all, now that we've done that, let's simplify what we can. And I think the only thing we can possibly simplify are what, just the 10s? So I have a negative x to the 8th minus 7 over 8. Oh, I'm sorry, x to the 10th. Yeah, sorry about that. Oops. I was just making sure you guys were following me. All right, let's see. Negative 7x to the, or negative 7 over 4x to the 4th minus 3x plus c. Okay, look, y'all, that's my original f of x, right? Because we had f prime to begin with, okay? There we go. Now, this part right here, look what this means, y'all. When f of negative 1 equals 27 over 8, all that means is that when x equals negative 1, y is 27 over 8. So what I'm going to do here is my y, or my f of x, I'm going to set that equal to 27 over 8. And everywhere we have the letter x, we're going to plug in what number? Okay, so let's do it to it. So look, right here, y'all, I'm going to put 27 over 8 equals negative 1 to the 10th minus 7 over 8, negative 1 to the 8th minus 7 over 4, negative 1 to the 4th, minus 3 times negative 1 plus c. Okay. So far, does that look okay in how we did the first part? I'm just plugging in everything. Okay, so let's take a look here, y'all. I got 27 over 8. Let's see. Question. Does anybody know what is negative 1 to the 10th power? Would that be a negative 1 or a positive 1? Positive 1. But with this right here, Steve, that's going to make it a what? Negative 1. Good. So look, we're going to have a negative 1 right here. Negative 1 to the 8th, wouldn't that also be a positive 1? But multiplying by negative 7 over 8, don't I have A negative 7 over 8? Okay. Negative 1 to the fourth is still positive 1, but times the negative 7/4 is a negative 7/4. What about negative 3 times negative 1? Positive 3 plus C. Y'all, what's the only letter that I don't know at this point? Okay. So, y'all, is there a way to do this on your calculator? I'm sure there is. Off the top of my head, I don't know, because I guess when I was in school, I did a lot of this stuff by hand. So this is my approach, y'all. If I was sitting where you're sitting and you're going to solve this problem, guys, even after teaching math for 25 years, I still hate having to deal with a ton of fractions like this. So my approach would say, look, let me multiply everything here. What's my common denominator anyway? Yeah, my common denominator is 8, right? That's the lowest common denominator for what I have. So look, let me multiply everything by 8. When I do that, let me scroll over here a little bit. I'm going to write over here, y'all, because I'm running out of room. That 8 is going to cancel, so I'm going to end up with a 27. 8 times negative 1 is a minus 8. When I multiply by 8 over here, that's going to cancel, so I still have a minus 7. When I multiply 8 over here, 4 goes into 8, how many times? 2. And 2 times negative 7 is a negative, good. Okay, what's 8 times 3? 24. And then 8 times C would just be 8C. Yeah. So look, y'all, look what I have. I have 27 equals negative 8 minus 7 minus 14 plus 24 plus 8C. This problem is much easier for me to solve because now I got real pretty numbers. Okay, that's negative 15 minus 14 is negative 29 plus 8C. Yeah, so that's 27 equals negative 5 plus 8C. So do y'all agree we got to add 5 to both sides? So 32 equals 8C. So then if we divided both sides by 8, what would we get, y'all? There you go. So now look, now I have C equals 4. So y'all, all I'm going to do now is where that C used to be, I'm going to plug in the number 4, and I'm going to write my answer right here. I'll do it in black. I'm going to put negative x to the 10th minus, you know what? I don't have enough room there. Let me write it somewhere else. I'll write it right here. Let's see. F of x, big and bold, negative x to the 10th minus 7 over 8, x to the 8th, minus 7 over 4, x to the 4th, minus 3x, and then finally a what? Plus 4 at the end. And there's my answer. So, y'all, again, is there an easier way to solve like this equation right here for the letter C without me having to do some of the stuff manually? I'm sure there is on the calculator. I don't know what it is off the top of my head. But my first approach was, because the number I was plugging in was negative 1, it was not a hard number for me to plug in, right? Like, because when you're thinking about it this way, when you're taking negative 1 and you're raising it to powers, if it's an even power, it's going to be a positive 1, and if it's an odd power, it's going to be a negative 1, right? So it's not going to be that hard to deal with. And then if I have fractions, multiply by the common denominator, now you got a bunch of integers, and it's easier to work with. You know what I mean? That's just my approach. And, yeah, it's a little tedious, but, at the same time, we're all in Calculus 1, so I think we can do that part. You know what I mean? Like, if y'all were in my college algebra class, I could see everybody going like, whoa, you know what I mean? But in Cal 1, I think we can manage that kind of definitely if y'all were in my remedial class, but I know you guys aren't remedial math books. But if you were, I can definitely see them doing that. But I think, we can manage this. And this part to me, y'all, wasn't that hard to do. Once we had the values, it was easier to combine the numbers, Uh-huh.
I just took the whole equation and said x equals negative 1 equals 6 and then took the top function and
It did it for you? Okay, there you go. Okay, take a look at this next one here, y'all. We have the integration, or we're integrating 4x to the fifth plus 3x to the fourth dx. Y'all, I want to just mention something. When you get to these problems in your homework, I want you to notice something that they're already adding at the end. They're already adding the plus c. So if you're entering your answer in and you're seeing the plus c, it's probably going to count it wrong because they already have the plus c there. I kind of wish they didn't do that because they're telling you, like, hey, don't forget the constant integration, but we've talked about it enough. So just be cautious when you're doing these problems, okay? So let's see, y'all. Look, we're going to have 4x to the, what power am I going to have on the top now? 6, and we have to divide it by 6. Plus 3x to what power now? 5, and we have to divide it by 5. Okay. Can we reduce any of those fractions? The first one, right? So wouldn't this just be a 2/3 x to the 6th plus a 3/5 x to the 5th? And then y'all, they already have the plus c there, so we don't have to worry about it. Yeah, and we don't have to find c. So y'all, in indefinite integrals, I think, I don't know if we do it, we might do it on Wednesday. If not Wednesday, then next week. We're going to talk about these things called definite integrals, okay? But right now we're dealing with indefinite integrals. In indefinite integrals, we always have that constant of integration. We always have that value of c, whatever it happens to be. Okay. Let's see. I think we got another one here. Yes. Okay, so we're going to go really slowly. And it says, consider the function f of t equals 8 secant squared t plus 5t to the third. Let f be the, or let capital F of t be the antiderivative of f of t with f of 0 equals 0. Then can we find capital F of t? Yeah, we can. So we're going to integrate again, y'all. 8 secant squared t minus 5t to the third dt. Guys, that when you're doing these integral problems, I always want to mention, just in general, they always have this part here. That just lets me know what I'm integrating with respect to. And a lot of times people say, well, look, it already has the t. Doesn't it just make sense that it would be the t? It does. Y'all, we're not going to do it in this class. You're not going to do it in Cal 2. I don't think you do it in Cal 2. Maybe you do. I don't think so. But when you get to like Cal 3, you have multiple integrals. So you have double integrals, triple integrals, and the expressions have multiple variables. So you might have a triple integral, and it'll have x, y, and z in it, and then you integrate with respect to x, you integrate with respect to y, and we'll get there when we get there. But I just wanted to mention that, right? And so, like right now, since we're just doing integrals, right? It's like anything else, though. We're just starting off with the calculus class. But because we are just starting off, it's a good habit to write down that little part because it knows what you're going to integrate with respect to, okay? So again, let's go really slow here. Let's see if we can't figure this out. What do I have to take the derivative of so that I get 8 secant squared t? Okay, 8 tangent squared t. Oh, tangent, yeah, sorry. 8 tangent t minus 5t to the fourth over 4th, okay, plus my constant of integration, okay? So look, y'all, this is my antiderivative function, right? Now, the second piece that they tell me is, look, f of 0 is equal to 0. So that means that this value here is going to be 0 when the value of t is 0. So 8 tangent of 0 minus 5 0 to the fourth over 4 plus t. So I already know that that part right there goes to 0. 5 times 0 to the fourth over 4. I know that's going to go to 0. Do I know the value of tangent of 0? Okay. Let's see. I'm in radians where I need to be. Okay. What's the tangent of 0? Tangent of 0 is still 0. Okay. So this piece is going to go away as well. So if that piece goes away and this piece goes away, then what's the value of c? Okay. So then my final answer here, y'all, is just going to be 8 tangent t 5/4 t to the 4. Okay. Because the value of RC ended up being 0. Does that make sense? So y'all, this problem was very similar to the one that we just did. It's just that in order for us to solve C, this one was a lot easier for us to solve for that value C, wasn't it? Right, because we plugged in 0 and it was equal to 0, and the tangent of 0 was 0, and 5 times 0 to the 4th is 0, so everything just kind of went away. Yeah, this one was just a little bit easier for us to do. Alrighty, let's see. All right, take a look at this one. The derivative of 5e to the x. So again, I know this is going to be a 5 because we've got a 5 right there. What's the integral of e to the x? E to the x. Again, y'all, they already wrote the plus c for me here, so I'm not going to worry about writing that plus c. Again, it was already written down. If it wasn't, then I would put the plus c, right? Okay. Let's see. Oh yeah, so look, take a look here, y'all. We have, it says f double prime of x, okay, equals 2x plus 3. Okay, so look what it's asking me to do. It's asking me to find f prime of x. Okay, we can do this. You're done with the second derivative. We want to know what the first derivative would be equal to. So we're going to integrate 2x plus 3 dx, right? Okay. So the integral of 2x would be x to the power 2 over 2. The derivative of 3 would be a 3x, and then I have my constant of integration. So everybody agree these 2's are going to cancel? So we're going to have x squared plus 3x plus c. This here, y'all, is my first derivative, right? Because we knew what the second derivative was. We now are finding the first derivative. They gave me another piece of information. They said that f prime of -1 was equal to 6. So this is going to be equal to 6 when x is equal to -1. Okay. So let's see if we can find our value of c. So I have 6 equals, let's see, -1 squared is this 1. 3 times -1 is a -3 plus c. So 1 minus 3 should give me a -2 plus c. Everybody agree we need to add 2 to both sides since it's a -2. So wouldn't we get 8 for my value of c? Okay. So look, y'all, all I'm going to do is I'm going to come back over here, and where this f prime of x is, in that value of c, I'm going to use the number 8. So right now, I'm going to write x squared plus 3x plus 8. Okay. Yes. So now, y'all, there's a second part. It says, can we find the original function at 1? In order for me to find the original function at 1, I need to find the original function. So now what we're going to integrate is we're going to integrate the first derivative. Okay. Okay. So look, let's go ahead and do that. The integral of x squared should be an x to the third. Everybody agree over 3? Okay. The integral of 3x should be a 3x squared over 2. The derivative of 8 should be an 8x. And then, y'all, I'm going to do this. I don't know. I'm going to call it D. Just because I've already used the letter C, I don't want to use the letter C again, right? This is my function f of x, right? So again, y'all, I just changed it to the letter D because we had already used C here. Then when anybody gets confused, like, hold on, which C am I using? Okay, we're using this one now. Look what it told me also. We also know that f of -1 is equal to -3. So this is what I'm going to do now, y'all. I'm going to come back over here, -1 to the third over 3, plus 3 times -1 squared over 2, plus 8 times -1 plus d is equal to, in this case, -3. All right. Okay, hold on, but let's finish this one first now. Sorry. Let's see. -1 to the third, y'all, is still -1. So I have a -1/3. Let's see. -1 squared is +1 times 3. So 3 over 2. 8 times -1. Very good. Plus d is equal to -3. Look, y'all, I'm going to do this. I'm going to think of all these as fractions. What do you think my common denominator is here? 6. Good. So let's do this. Let's multiply everything here by 6 over 1, or by 6, and we can then solve for the letter d. Okay, so one piece at a time. 3 goes into 6, and 2 times -1 is a, 2 goes into 6. 3. Very good. And 3 times 3 is going to give me 9, right? 6 times -8 should be a -48. 6 times d should be 6d. And then 6 times -3 should be a -18. So right here, y'all, I'm going to combine my negative numbers together. -2 and -48 is a -50, plus 9 plus 6d equals a -18. Okay. -50 plus 9 should be something like a -41, plus 6d equals -18. Okay. I'm going to go ahead and add 41 to both sides. Got my calculator. Let's see. -18 plus 41, 23. And then I'm finally going to divide everything by 6. Okay, so I get d equals 23 over 6. Okay, so let's see. Y'all, what that's telling me now, remember, here was my original function, right? So I'm going to write that out now. I'm going to write f of x equals, let's see, x to the third over 3 plus 3x squared over 2 plus 8x plus 23 over 6, right? So far, we okay in how we came up with those numbers? Okay. And y'all, I want to show you something. Look what the question is actually asking me to do. Yeah, the question is asking me, can we find f of 1? You know what? We can. And the way I would do this, if I was sitting where you are sitting, say this out, I'd go to y equals. I'd put x to the third. I'll probably have to put that in parentheses because of just the operation. Parentheses x to the third divided by 3, and then plus, let's see, parentheses, I'm going to go 3x squared over 2 plus 8x plus 23 over 6, like this. Okay, so I'm just entering the function in, y'all. I'm going to go ahead and hit enter. I'll quit this. I'll go to my y bars. I'll go to my function. We're trying to find the value at the number 1. And I'm coming up with 13.66666. Okay, all that kind of funky stuff. Yeah, so that's 31.6. It repeats. So that would actually be 13 2/3. which is 41 over 3, right? But again, that's how, yes, ma'am. Into a fraction? Yeah. So the way you normally do it here, okay, so when you get this answer here, what you would do is go second, and then right above the negative sign, do you see where it says answer? Okay, you're going to do answer, and then right here where it says math, look at number 1. Do you see number 1 says fraction? You're going to click that one. I don't know if it's actually, oh, look, it did it. Pretty neat. There you go. And there's how you convert it to a fraction. And guys, just so that you, so yes, now, Jennifer, one thing I will say is that, and I don't know, Steve, you have the same calculator we have, right? So like John's calculator obviously is more advanced. And then I know there's like, and guys, I have like 4 of them, and my stepdaughters have them. But I don't know if I have any more at the house. If I do, I'll bring one in. And guys, I'm not advocating at all go buy a new calculator. I don't think y'all need to do that. I will say though that sometimes with some of the decimals, if you do the answer frac, it just doesn't convert them. You know what I mean? Like sometimes it won't do it. And like, maybe John's will because it's a more powerful type calculator and all that kind of stuff. You know what I mean? And he can do updates and all that kind of stuff. And like our calculators, I mean, you can't even, like I don't think we can do updates on these. They're a little bit older, right? So again, if it doesn't work, and yeah, if it still gets you as a decimal, I don't necessarily know that my open math is going to be that picky. It's probably pretty lenient, right? So far as we've been doing the problems, it's been pretty lenient. So guys, let me ask you a question. How did antiderivatives thing? It's for the most part, y'all, it's intuitive because we've taken derivatives, we've been doing derivatives since chapter 3. So a lot of it, the antiderivatives become intuitive. I'll tell you the parts where we sometimes have issues are, and let me see if I can do it this way, y'all. Let me do it like this. Let me see if I can give you guys a rule for e to the ax. Okay. Like if I want to integrate e to the a times x, I want you to think about this for a minute. I'm going to think of the derivative. I'm going to think of the derivative of e to the power ax. A is just going to be some constant, y'all. So a can be the number 3, a can be the number -5, a can be the number 1/7. Okay, it doesn't really matter. If I'm taking the derivative of e to the ax, do you guys agree that I would get e to the ax, but then I still have to take the derivative of the angle? And the derivative of the angle would just be, what, a, right? Okay, so then to take the integral of e to the ax, still, the integral of e to the ax would be 1 divided by a e to the ax plus c. Okay, because integrating, I'm going to have to do the opposite, right? I'm going to have to divide by that same number. And I want you to notice something here. If I take the derivative of this, I get that a right there. But that a with this a down here would end up canceling each other out. Okay, so this gives me a general formula for taking the derivative of e to the ax. So that now if I said, look, what's the integral of e to the -3x? Then we could say it's going to be e to the -3x divided by -3, right? Because it's, or I can write it like this. Let me write it the way I wrote it here. Oh, man. That would be my answer, right? Because it's always going to be 1 over that number right there. Okay. And now it can take the derivative of any of those kind of functions like that. So again, y'all, this just gives me a general formula that I can use when I'm integrating, okay? If I have the e to the a power x, okay? It'll always work that way. So, yo, just a heads up, again, before we leave, let me do this real quick. Let me go ahead and close that up because we don't need it anymore. That was 3.6, that was from a long time ago. Let's see, week 11. Okay, so look, y'all, the homework for 4.10, it's already open. It's due a week from tonight. The quiz, y'all, the quiz should, I think the quiz opens at the end of class today. Let me double check. Let's see, maybe not. I'm just curious if it'll actually open up. Or does it open at the end of class? Okay, yeah, it'll be open at 2:50. But it's not due until next Wednesday, okay? So y'all, 10 questions, okay? Take your time with it. No rush, 10 questions over stuff in chapter 4. Use your notes. Guys, this afternoon, since we just finished up chapter 4, just a heads up, where is it? Here we go. Where we have like formulas and chapter notes, and I click on this right here, like there's chapter 2 and chapter 3. Today I'm going to upload chapter 4. Since we've already done all of chapter 4, I'm going to put it in one document so that you guys, if you need to, you'll have it in one document right there, okay? And then on Wednesday, y'all, we'll start with 5.1. Sound good? Okay, y'all, so I'm going to go ahead and stop recording. Again, I will